Yesterday, we were discussing exercise 1.3. We completed first Roman and second Roman problems. Now, I continue the problems on exercise 1.3 in real numbers. You can refer the page number 13. We use theorem 1.2 to solve the problems. Now, what is theorem 1.2? Theorem 1.2 is the fundamental theorem of arithmetic. What is the statement of fundamental theorem of arithmetic? According to the statement of fundamental theorem of arithmetic, every composite number can be expressed or factorized as a product of primes. And this factorization is unique apart from the order in which the prime factors occur. Now we will discuss the problems in detail. Real numbers, class 10, exercise 1.3, page number 13. We continue the problems in this exercise. Write the following. Write the following rationals in decimal form in decimal form first problem 23 by 13 by 25 13 by 25 13 by 25. Now 25 equal to 5 square. We want to get the form 10 square in the denominator. To get 10 square in the denominator, 5 square must be multiplied by 2 square. 5 square must be multiplied by 2 square. So the given problem can be rearranged as 13 by 25 equal to 13 by 5 square equal to 13 by 5 square multiplied by 2 square by 2 square. This is equal to 13 multiplied by 4 by 10 square equal to 52 by 100 equal to 0.5. Therefore, 13 by 25 equal to 0.52. It is a terminating decimal. It is a terminating decimal. We can write it. It is a terminating decimal. 13 by 25, it is given 25 can be written as 5 square. We want to get a 10 square form in the denominator. So this is why, because we want to get 2 power n, 5 power m in the denominator. We want to get the form 2 power n, 5 power m in the denominator. So that is why we multiplied and divided by 2 square. 13 by 5 square multiplied by 2 square by 2 square. This is equal to 52 by 100. So the answer is 0.52. Now we consider the next problem. Fifteen by 16. 15 by 16 equal to 3 multiplied by 5 divided by, we find prime factors for 16. 2 8s, 2 4s, 2 2s. So 2 power 4. Now we want to get the form 10 power 4 in the denominator. So 2 power 4 must be multiplied by 5 power 4. So this is equal to 3 multiplied by 5 by 2 power 4 multiplied by 5 power 4 by 5 power 4. So in the denominator we get 10 power 4. The numerator 3 multiplied by 5 power 5. This is equal to 5 multiplied by 5, it is 25. 25 multiplied by 5, this is 125. So this is 5 square. This is 5 cube. 5 power 4 equal to 5 cube multiplied by 3. That equal to 125 multiplied by 5. It is not 3, 5. So we get this is equal to 625. Now 5 power 5 equal to 625 multiplied by 5. That equal to 3125. Again 5 power 5 multiplied by 3 equal to 3125 multiplied by 3. This is equal to 979375. So we can write 9375 divided by 10 power 4. So this is equal to 0.9375. 0.9375. So what students must remember is we have converted the given number into the form of a terminating decimal. So we want to get 10 power n in the denominator. We want to get 10 power n in the denominator. To get 10 power n, 10 power 4 in the denominator, we multiplied and divided by 5 power 4. Why? Because we have 2 power 4 in the denominator. So the 2 power 4 must be multiplied by 5 power 4 to get 10 power 4 in the denominator. So this is how we converted the given rational number into a terminating decimal number. Now we write it, this is a terminating decimal number. Terminating decimal number. This is a terminating decimal number. Now, third problem, 23 by 2 cube 5 square. We want to get 10 power n form in the denominator. So, to get 10 power 3 in the denominator, 2 power 3 5 square must be multiplied by 5. So, we must multiply by 5. This is equal to 23 by 2 5 square multiplied by 5 and divided by 5. This is equal to 115 by 2 power 3 multiplied by 5 power 3 equal to 115 by 10 cube. This is equal to 0.115. Again, this is a terminating decimal. This is a terminating decimal. This is terminating decimal number. Here, students must remember that the denominator should be converted into the form of 10 power n. Here, 10 power 3 we want to get. To get 10 power 3, we have multiplied and divided by 5. So that we get 0.115. So this is without division, because in the question they asked us to use the theorem. It is by using the theorem. Now, next fourth problem. 7218 divided by 3 square 5 square, 3 square, 5 square. Now we find the prime factors for 7218. 3 twos, 6, so 3 fours, 0, 6. Again 3 eights, 0, 2. Now we divide it by 2, so it is 401. It is 401 is a prime number. I will take a class on prime numbers, and I will explain you how to find that a given number is a prime number. I will explain this concept separately. 401 is a prime number. So this is equal to 2 multiplied by 3 square multiplied by 401 by 3 square multiplied by 5 square. So on cancellation we get this is equal to 2 multiplied by 401 by 5 square. Now we want to get 10 square in the denominator. To get 10 square in the denominator, 5 square must be multiplied by 2 square. To get 10 square in the denominator, we must multiply by 2 square. Therefore, 2 multiplied by 401 by 5 square multiplied by 2 square and divided by 2 square. So here we multiplied and divided by 2 square. Why? Because we want to get 10 square in the denominator. We want to get 10 square in the denominator. This is equal to 2 power 3 multiplied by 401 by 10 square equal to 8 multiplied by 401 by 10 square equal to 3208 by 10 square. This is equal to 32.08. We get the answer 32.08. This is terminating decimal. This is terminating decimal. We get terminating decimal. 7218 is given. We have found the prime factors for the 7218. We got 2 multiplied by 3 square multiplied by 401. Denominator, in the denominator we have 3 square multiplied by 5 square. So 3 square gets cancelled. We get a 2 multiplied by 401 by 5 square. Again, we want to get 10 square form in the denominator. To get a 10 square form in the denominator, we multiply and divide by 2 square. Therefore, we get 10 square in the denominator, and finally we get 3208 by 10 square. Therefore, the answer is 32.08. We continue. Next problem. Fifth problem. 143 by 110. Now we find prime factors for 143. So we divide it by 11, 11 ones, 11 threes. So for 110, 110 to 55 is 5 11s. Therefore, 143 by 110 is equal to 11 multiplied by 13 divided by 2 multiplied by 5 multiplied by 11. Now 11 gets cancelled. We get 13 by 10. This is equal to 0. Not 0. 1.3. 1.3. Again, this is a terminating decimal. Terminating decimal. Students must remember that we want to get 10 power n in the denominator. So this is how we have found the decimal expansion form for the given rational number in the form of p by q. Now, fourth Roman problems. Roman 4. The decimal form of some real numbers. The decimal form of some real numbers are given below. In each case, decide whether decide whether the number is rational or not. The number is rational or not. If it is rational, if it is rational, and expressed and expressed in form p by q, What can you say about what can you say about the prime factors of Q? First problem, 43.12345678 9. Now we read the problem. The decimal form of some real numbers are given. So a number is given to us. It is in the decimal form. In each case, decide whether the number is rational or not. So by observing this decimal number, we should say whether it is a rational number or irrational number. And we must give the reason also. How can we say that it is a rational number, or if it is not rational number, if it is an irrational number, how can we say that it is an irrational number? We must give the reason also. If it is rational and can be expressed in P by Q form, then now what can you say about the prime factors of Q? Now we answer to this question. So let it be x. Let x equal to 43.12345678 9. So what is the observation? This is a terminating decimal number. So now we write x is a terminating decimal number. Hence, hence it is a rational number. Hence, so we know that a terminating decimal number is a rational number. Hence, it is a rational number. It is a rational number. Now, if this x equal to, if this x can be represented as P by Q, that means 43 point if x equal to P by Q, then we have got a terminating decimal here, terminating decimal number. Then Q is of the form, Q is of the form 2 power n 5 power m. So this is theorem. We have the theorem 1.4. This is theorem 1.4. This is a theorem 1.4. If x equal to p by q, here what we must write is we must write about p and q. Q is not equal to 0. Here q is not equal to 0. Now we consider the next problem. Second problem, 0.1201 to 001 to 00012, again 4 zeros, and so on. So I suppose that this is equal to x. The given number is x. The given number, the given number the given number is a non-terminating. It is a non-terminating and non-recurring 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 decimal number. Hence, so if the given number is a non-terminating and non-recurring decimal number, then we say that it is a rational number. Therefore, hence it is a irrational number. It is a, hence it is an irrational number. Hence it is an irrational number. Now we also give some explanation. This number cannot be expressed in p by q form. This irrational number, cannot be expressed in a p by q form, where q is not equal to 0, p comma q are integers. So then there is no question of how the denominator q can be expressed. There will be no such question, because we cannot express the denominator. We cannot express the given irrational number in p by q form. Therefore, this irrational number cannot be expressed in p by q form. The given number is a non-terminating and non-recurring decimal number. Now we consider the third problem. X is equal to 43.9 1, 2, 3, 4, 5, 6, 7, 8, 9 bar. So this is a non-terminating but a recurring decimal. X is a, otherwise I will write the given number x. The given number x is a non-terminating and recurring within brackets we write repeating decimal number. We know that a non-terminating and a recurring decimal is a rational number. So x is a rational number. The given number x is a rational number. Therefore, it is a rational number. It is a rational number. Now, if x equal to p by q, where q is not equal to 0 and p comma q are integers, then q is of the form q is not of the form of the form 2 power n 5 power m. So when the denominator is not in the form of 2 power n 5 power m, then only we get non-terminating and recurring decimals. Then only we get non-terminating recurring decimals. So we must give the reason also. We have observed that the given decimal number is a non-terminating recurring decimal, and hence we can conclude that it is a rational number. Now we have theorem 1.5. So we must write it as theorem 1.5. By theorem 1.5, what we can say is that if we are given a rational number p by q, and if it is not of the form 2 power n 5 power m, then it is a non-terminating and recurring decimal. Now we study about irrational numbers. Next concept is irrational numbers. Students can refer the page number 13. Irrational number. Irrational number. If a real number cannot be expressed in the form of p by q, where q is not equal to 0 and p and q are integers, then we say that such numbers are irrational numbers. In other words, If a number is not a rational number and it is a real number, such real numbers are said to be irrational numbers. Now we note down the statement. A real number is called irrational number. Irrational number. And it is denoted by Q dash or S. Q dash or S. If it cannot be written, if it cannot be written in the form P by Q, where Q is not equal to 0, P and Q are integers. We can take some examples. 2.3175268950 and so on. So this is not terminating decimal. It is non-terminating, non-recurring decimal. 13.2375820316 and so on. So when do you say that it is an irrational number? This is a non-terminating and non-recurring decimals. Recurring decimals are irrational numbers. Irrational numbers. So this is about irrational numbers. And when we consider some more examples. Square root of 2, square root of 3, square root of 15, root 2 by root 3 by root 11 and so on. So these are irrational numbers. So that means what we observe here is the square root of the square root the square root of a non-perfect square number. Non-perfect square number. Non-perfect square number is an irrational number. Is an irrational number. Then the question arises, what do you mean by a perfect square number and a non-perfect square number? So perfect square number, I will give some examples. What are perfect squares? Perfect square numbers, non-perfect square numbers. So we consider these two. We consider some examples for these perfect square numbers and non-perfect square numbers. Consider 1 square equal to 1. So 2 square equal to 4. 3 square equal to 9. 4 square equal to 16. 5 square equal to 25. 6 square equal to 36. All these are examples for perfect square numbers. 7 square equal to 49. 8 square equal to 64. 9 square equal to 81. 10 square equal to 100. Now 2 is non-perfect number. 3 again 5, 6, 7, 8. So 9 is missing. 9 is a perfect square number. 10, 11, 12, 13, 14, 15. All these are non-perfect square numbers. And 16 is a perfect square number. 17, 18, 19, 20, 21, 22, 23, 24, 25 is a perfect square. 26, it is a non-perfect square number. 27, 28, and so on. So you must understand the difference between a perfect square number and non-perfect square number. Now, after understanding the definition of a perfect square number, a non-perfect square number, now we consider the square root. The square root of 2, 2 square, that equal to 2. Square root of 4 equal to 2. Square root of 9 equal to 3. Square root of 16 equal to 4. Square root of 25 equal to 5. So we considered positive values only. Here we considered positive numbers, otherwise positive integers. Integers in examples. So what about the non-perfect square numbers? Square root of 3, square root of 5, square root of 6, square root of 7, square root of 8, square root of 10, and all this. So here these are rational numbers. These are the square root of perfect squares are rational numbers. The square root of non-perfect square numbers are irrational numbers. Students must understand this difference. So, all square root numbers are not irrational numbers. Only the square roots of non-perfect squares are irrational numbers. The square root numbers of the square root of a perfect square is considered as a rational number. Why? Because we get only the positive integers. Here we considered only positive integers in the examples. Why? Because here you must remember that square root of this is not square root of x square equal to plus or minus x. So here square root of 25 equal to plus or minus 5. Square root of 36 equal to plus or minus 6. Square root of 49 equal to plus or minus 7. So square root of 64 equal to plus or minus 8. Square root of 81 equal to plus or minus 9. Square root of 100 equal to plus or minus 10. We must consider plus or minus. If x is real number, if x is a real number, then this is the case. Now we consider a theorem and based on this theorem we will try to prove certain properties of irrational numbers. Theorem 1.6. Theorem 1.6. This is page number 813. Page number 13. Let P be a prime number. Let P be a prime number. Let P be a prime number if P divides a square. If P divides a square where a is a positive integer, a is a positive integer, then P divides a. Then P divides a. To understand the statement of this theorem, we consider some examples. P equal to 2, a square equal to 64. Here 2 divides 64. That implies if a square equal to 64, then what is a? A equal to 8. 2 divides 8. This is the meaning of the statement of theorem 1.6. Now we consider some examples to understand the statement of this theorem. So this is first example. This is example 1. Here 2p is a prime number. P equal to 3. I considered a square equal to 81. Then a must be equal to 9. 3 divides 81. That is a square. Implies 3 divides 9. And we consider another example. P equal to 5. A square equal to 625. A equal to 25. Because square of 25 is 625. 25 square equal to 625. So here 5 divides 5 divides 625. That implies 5 divides 25. So if p divides p divides a square implies p divides a, and we can consider another example. If this is not we consider p value, p equal to 2, a square equal to 1024, a equal to 32, because 32 whole square equal to 1024. 2 divides 1024 implies 2 divides 32. So from all these examples, what we can understand is that so now we understand the meaning of the statement p divides a square. P divides A square implies P divides A. This is very important result, and we use this result in proving some problems. Now we consider some problems, and these problems are very important from the examination point of view. First problem, show that show that square root of 2 is irrational. Is irrational. Show that square root of 2 is irrational. First we assume that square root of 2 is a rational number, and as a result we get a contradiction. When we got contradiction, we conclude that our assumption is wrong, and finally conclude that root 2 is an irrational number. So let us start our assumption. Let us assume root 2 is rational. Square root of 2 is rational number. If R and S, if it is a rational number, if it is a rational number, then square root of 2 equal to A by B. Here A and B are co-primes. Co-primes. Now the question arises, what do you mean by co-primes? If the HCF of two numbers is 1, then we say that the two numbers are co-primes. That is HCF of A comma B equal to 1. So co-primes means the highest common factor of A and B are equal to 1. And here A and B are integers and B is not equal to 0. Where A and B are integers, B is not equal to 0. This is our assumption. That means if the square root of 2 is a rational number, every rational number can be expressed in the form of P by Q. So I have written so if square root of 2 is a rational number, then it can be expressed in the form of A by B. Here A and B are co-prime numbers. Now square root of 2 equal to A by B, that implies A equal to square B multiplied by square root of 2. B multiplied by square root of 2. Squaring on both sides, squaring on both sides, squaring on both sides, A square equal to B square root of 2 whole square, that equal to 2B square. So we got A square equal to, we got A square equal to 2B square. We got A square equal to 2B square. Now the right hand side 2B square is divisible by 2. So left hand side A square must also be divisible by 2. So here I write 2B square is divisible by 2. Is divisible by 2. Hence A square is divisible by 2. Hence A square is divisible by 2. Because why? Because if right hand side is divisible by 2, then the left hand side is also divisible by 2. Why right hand side is divisible by 2? Because 2 is there on the right hand side. When 2 is there on the right hand side, we can say that it is divisible by 2. So now if 2 divides A square, here 2 is a prime number, remember, here 2 is a prime number, then 2 divides A, then 2 divides A. This is theorem 1.6. This is theorem 1.6. This is by theorem 1.6. This is theorem 1.6. If 2 divides A, then we can write A equal to 2 divides A, we can write then we can write A equal to 2C for some integer C. For some integer C. This is we take some examples to understand this concept. How can we write this A equal to 2C? Here, suppose 2 divides 8. Then 8 can be written as 2 multiplied by 4. If 2 divides 16, if 2 divides 16, then 16 equal to 2 multiplied by 8, I can write. If 2 divides 20, then 20 equal to 2 multiplied by 10. So here This is C, C, C. This is taken as A. A equal to 2C. Now, students, you try to understand this concept. If 2 divides A, then A equal to 2C. We can write it. A equal to 2C. If 2 divides 16, 16 can be written as 2 multiplied by 8. If 2 divides 8, 8 can be written as 2 multiplied by 4. And if 2 divides 100, 100 is equal to 2 multiplied by 50. So this is the important concept. All the students must understand this concept. If 2 divides A, if 2 divides A, if 2 divides A, then we can write A equal to 2C. This is very important concept. You need not try to by heart this concept. You must try to understand the concept by these examples. So I keep all these examples in a box. You need not write in the proof. This is only examples to understand this concept. So A equal to 2C. Now we got A equal to 2C. A equal to 2C. Squaring on both sides. Squaring on both sides. A square equal to 2C whole square. That equal to 4C square. That equal to 4C square. But we know that A square equal to, but but A square equal to 2B square. That implies in place of A square I can write 4C square. I can write 4C square. 4C square equal to 2B square. That implies C square equal to 2C square equal to B square. Here again we can conclude that 2C square is divisible by 2. 2C square is divisible by 2. 2C square is divisible by 2. Hence, B square is divisible by 2. So when 2C square is divisible by 2, the right hand side B square must also be divisible by 2. Now we apply theorem 1.6. By theorem 1.6, if 2 divides B square, then 2 divides B. Right. So we got that in the earlier so here we got that 2 divides A. Here we got that 2 divides A. 2 divides A, and now we got 2 divides B. That means We write that step. We got that 2 divides both A and B. So from this 2 is common factor. Common factor, it implies it implies it implies that it implies that 2 is a common factor of both A and B. So we got this result. 2 is common factor for both A and B. This is a contradiction. This is a contradiction. Contradiction to our assumption, that square root of 2 equal to A by B, where A and where A and B are co-primes. A and B are co-primes. Co-primes in the sense that highest common factor of A and B is equal to 1. Now we got that common factor of A and B equal to 2. So this is a contradiction. Since we got this contradiction, we conclude that our assumption, hence our assumption that square root of 2 equal to A by B is wrong. That is square root of 2. What is the assumption? Square root of 2 is a rational number. Rational number. So now we conclude that our assumption that square root of 2 is rational is wrong. Hence, square root of 2 is irrational. Students, I would like to explain this problem now. You try to understand this concept. Based on this model, I would like to explain some more problems. Show that square root of 2 is irrational. To show that square root of 2 is irrational, we suppose that we assume that square root of 2 is a rational number. If square root of 2 is a rational number, then we can write square root of 2 in p by q form. Here we have written in the form of a by b, where a and b are co-primes. Then what do you mean by co-prime numbers? If the highest common factor of two numbers a and b is 1, then we say that the two numbers a and b are co-prime numbers. Here a and b are integers. Now, if we can write the square root of 2 equal to a by b, then on cross multiplication, we get a equal to b multiplied by square root of 2. A equal to b multiplied by square root of 2. Squaring on both sides, we get a square equal to 2b square. Squaring on both sides, we get a square equal to 2b square. On the right hand side, we have 2b square. On the right hand side, we have 2b square. 2b square is divisible by 2. Why? Because 2 is there on the right hand side. So it is very clear that 2b square on the right hand side is divisible by 2. When right hand side is divisible by 2, we can conclude that the left hand side term a square is also divisible by 2. Since the left hand side a square is divisible by 2, by applying theorem 1.6, if p divides a square, then p divides a. Theorem 1.6 states that if p is a prime number and a is any positive integer, then if p divides a square, then p divides a. Here 2 is a prime number. Since 2 is a prime number and 2 divides a square implies that 2 divides a. From this we can write a equal to 2c. To understand this concept, we have considered several examples. If 2 divides 20, if 2 divides 20, then 20 can be written as 2 multiplied by 10. If 2 divides 16, we can write 16 equal to 2 multiplied by 18. 8. If 2 divides 8, we can write 8 equal to 2 multiplied by 4. If 2 divides 100, it can be written as 100 equal to 2 multiplied by 50. So, if 2 divides a number a, then we can write a equal to 2c for some integer c. We can understand this is a statement by observing these examples. A equal to 2c, we have this squaring on both sides, a square equal to 4c square. But a square equal to 2b square, we have this statement in the starting, a square equal to 2b square. So, but in place of a square, I can write 4c square. Now, 4c square equal to 2b square. On cancellation, we get 2c square equal to b square. Here, 2c square is divisible by 2. 2c square is divisible by 2. Hence, I can conclude that b square is divisible by 2. This is why, because 2c square is equal to b square. Now again, if by applying theorem 1.6, if p divides a square, then p divides a. Here 2 is a prime number. 2 divides b square. If 2 divides b square, then by applying theorem 1.6, we can conclude that 2 divides b. Now, we got that 2 divides both a and b. 2 divides a and 2 divides b. That means 2 divides both a and b. It implies that 2 is a common factor of both A and B. A and B have common factor 2. This is a contradiction to our assumption that A and B are co-primes. In the starting, we assumed that square root of 2 equal to A by B. If square root of 2 is a rational number, then we can express square root of 2 in the form of A by B, where A and B are integers and the highest common factor of A and B is equal to 1. That is, A and B are co-primes. Now we got that 2 is common factor of A and B. This is contradiction to the assumption that A and B are co-primes. We got this contradiction. Why? Because our assumption is wrong. So our assumption that the square root of 2 is a rational number is wrong. If a number is not a rational number, then it must be an irrational number. So finally we conclude that since we got a contradiction to our assumption that square root of 2 is rational, we conclude that the square root of 2 is a irrational number. Dear students, tomorrow we solve some problems based on this model. We find we will show that the square root of 5 is an irrational number, square root of 3 is an irrational number, square root of 3 multiplied by root 2. 3 root 2 is an irrational number. We show that 5 minus root 3 is an irrational number. We show that root 2 plus root 3 is an irrational number. And there are several important concepts in exercise 1.4 of page number 16. You should learn these concepts by concentrating more, and you should practice these problems. Without practice, mathematics, by just reading mathematics, you cannot get a hold on mathematics. So to get a perfect command or mathematics in the present syllabus, you must practice and practice. Thank you all students. Thank you very much.